Hello, I'm Lily Darrow,
I'm Laura Fraher.
And I'm Leo Bormann.
and the title of our presentation is Taking the Problem Out of Word Problems. So we're going to ask you to go ahead and close your eyes for a second and imagine you're 13 years old again. Take a deep breath in, deep breath out. Feel your body shrink, your anxieties heighten. Okay, so maintain this mindset, open your eyes, and try to solve this math problem. Ravel has 15 dogs. Owen has 2 dogs. How many dogs do Ravel and Owen have together? Yeah, Laura?
17 dogs.
Correct. The answer is 17 dogs. Aren't word problems easy? Okay, so now in the same 13-year-old mindset, try and solve this math problem. Kate bought 486 oranges and split them with her 2 siblings. How old is Kate? Leo?
Is Kate 12?
I'm sorry, Leo. Kate is 13.
That's hard.
So you guys might have thought the second problem was tricky, and yes, it's purposely impossible to solve, but this is how students and sometimes adults can view word problems. They just don't understand what the word problem is asking for, and all word problems look this difficult to them. So in this presentation, we are going to discuss why students might find word problems difficult, and then some strategies we can use in the classroom. So first, we're going to go through some reviews on the importance of reading comprehension in solving word problems. Then we're going to discuss the possible mediators between reading comprehension and successful word problem solving. So why reading comprehension improves word problem solving, success in students. And then last, we're going to talk about some evidence-based word problem solving practices to implement in your own classroom.
Perfect. So when we started our study, we kind of explored how they were studying the correlation between literacy and word problems. One of our first studies is actually with college-age students from 18 to 21. So they took 96 undergraduate students. They ran them through a couple word problems, and it focused on specific language. So in their first phase, they had to find a solution to a mathematical word problem containing relational statements. In their second phase, students were given information about 2 variables and asked to create a statement expressing that relation. So in these kind of phases, they solved for a word problem, but then also they were given kind of like an algebraic expression that showed correlation, and they were tasked with creating a word problem. So they kind of got to see both sides of how the undergraduates tackled these problems. So this before we go into the results of it, we're going to look at what inconsistent versus consistent word problems are, or phrases. And this is something that we can teach our students, which can oftentimes be actually harmful to their learning. So when you're looking at the keyword like altogether, you might have been told, oh, altogether, that means that we need to do addition. But this graphic states examples where that's not always the case. So it says that Alice bought 4 cartons of eggs with 12 eggs in each carton. How many does Alice have altogether? So if you were showing your students that altogether meant addition, they might say that they have 16 eggs, when in reality that's 4 cartons of 12. It's a multiplication problem, and they'd have 48 eggs in total. So below are other keywords like more, fewer, left, each, double, share, and just examples of how those are not always going to fit like the stereotypical associated operation. So this is what our study showed. It's the students' miscomprehension. So there wasn't errors in their mathematical solving. What the problem was this consistent and inconsistent language. So if you look at the bottom axis, it says arithmetic operation, and you have they studied multiplication and addition. And then on the other axis is the probability of error. So in the light gray, that is our consistent language. And then in kind of the black is the inconsistent language. So students in this study ran into problems, and the probability of error was much higher when there was inconsistent language. So they saw those keywords like double or altogether and assumed the operation, when in reality, when it's consistent language, they did much better because they were just looking for the phrases and the numbers that they needed and solving straight from there. So you can see how that inconsistent language is a huge challenge in the miscomprehension, because the students aren't actually understanding what the problem's saying. They're just looking for those key words. So why is there this disconnect? We just talked about the inconsistent versus consistent math language. They saw more success when the word problem phrase was reiterated, as well as the phrases that they were looking for were consistent with that operation. And this all goes back to in literacy decoding and understanding what your reading is asking and what they need to do from there. This problem is not just with the graduate students. It's been done with students of all ages. One that we're highlighting is that they took 215 fourth graders. And in this study, they systematically evaluated them as good readers or poor readers based off of standardized tests, how they're doing in the classroom, what the teachers and faculty are observing. So when they were put into the good reader and the poor reader categories, they then were run through word problems with them and evaluated the accuracy of them. So in our graphic over here, there's math word problems, and then reading comprehension is what they were both focused on. And there is a huge disparity between how the good readers did as compared to the poor readers, which this is just another study that emphasizes that importance of literacy for the students. Just a quote from the article said, even after controlling for the level of technical reading involved, performance in math word problems was still related to reading comprehension, suggesting that both of these skills require overall reasoning abilities. So just even on top of literacy and how students can do in comprehension of word problems, they have to have that reasoning ability too. So there's a lot of factors that tie into our students and how they solve word problems. So what insight does this show us as educators? Again, this shows the strong connection between literacy comprehension and accuracy in solving word problems. If a student is more affluent in ELA, they're definitely more likely to see success when it comes to word problems and higher application of their math reasoning. The issues individuals can face is solving for what specifically a problem set is asking for, rather than just cherry picking those key phrases that we've all grown up learning about and associating with different operations.
So given how important reading comprehension is for successful word problem solving, we sought to discover what's the mediator between reading fluency and successful word problem solving. So one study that looked at this was called Pathways to Word Problem Solving, and they assessed 139 Chinese third graders on 4 different math components. So one was knowledge of arithmetic concepts, second was their reading fluency, third, schema construction, meaning the structure behind word problems, and then fourth, knowledge of math vocabulary. And they looked at the relationships between them. So before we go into their findings, we're going to explain what schema construction is and how they assess that. So schema construction is the structure behind word problems. So one example of an additive schema is part-whole schema, also known as total or combine. So this is the structure would be part 1 plus part 2 equals a total. And a word problem that follows the structure is Sam has 2 cookies, Allie has 3 cookies. How many cookies do they have all together? And so you have 2, which is one part, 3, another part, and then it equals the total, which would be 5. To assess this construction, they gave students the word problem, and they had to pick A, B, or C, which are all different schema, and then fill in the numbers in that schema. So if you look at this word problem, a toy car costs $30, a deck of playing cards costs $10. If Peter wants both, how much does he need to pay? The correct answer would be A, and they'd put 30 right here, 10 right here, and then in total they'd put 40. Another thing they assessed was knowledge of math vocabulary. And to assess this, they had a word problem with an illustration. So here we have the illustration, and here we have the word problem, and they have blanks in the word problem the student has to fill in. So there were 7 apples in the basket, blank, now there are 9 apples in the basket. And so the student has to look at the picture and find out that it would be B, a person put more apples in the basket, and how many apples did the person put. What they found in the study was that, yes, what they just assessed, schema construction and the knowledge of math vocabulary were the mediators between this reading fluency and the successful word problem solving. Again, these are 2 more studies that talk about schema-based word problem interventions. So this 2010 study with 270 second graders found that schema-based interventions were better than business as usual instruction for helping students. And in this 2021 study with 191 first graders, they looked at 4 different interventions, and they found the schema-based word problem interventions were the best, but especially most effective was the schema-based word problem interventions with embedded language instruction, with them teaching those math vocabularies. So that outperformed schema-based interventions, structured number knowledge interventions, or simply the control note interventions at all. So looking at these studies, we saw there was a gap in how these interventions work for students with math learning disabilities. And they also mostly looked at those simple schema construction, like just one addition or multiplicative schema, not multi-step problems. So to look at this study assessed 4 8th graders with diagnosed learning disabilities. They gave them an intervention. It was a 35 to 40-minute scripted lesson by one teacher with explaining 6 word problems. And they included all these different forms of instruction: modeling, discussion, guided practice, feedback, and independent practice. And what they found was pretty remarkable. Here we have the different students: Sarah, Tony, Percy, and Andy. And on the y-axis, we see percent corrective word problems. And then here are the different types of word problems: one-step and multi-step, varied, multiplicative, and multi-step. And you can see that the accuracy actually jumped to 100% in most of these cases. The light gray was pre-treatment and the black is post-treatment. And so you can see they really jumped. What's amazing about this study was the teacher did not teach them multi-step problems, but they were able to transfer their skills and be able to solve these multi-step problems with 100% accuracy. And for Sarah in particular, this effect lasted after 10 weeks. Some limitations to consider though for this study was it's only a small sample size. There are only 4 students, and there was only one teacher instructing this. So we're curious about the transfer of this instruction with different teachers.
So we kind of already discussed the importance of creating visual schematic representations and how that's a possible mediator between reading comprehension and successful word problem solving. And so here's an example of a visual schematic representation versus just a normal pictorial representation. So students see a word problem, they're asked to draw the representation they had in their mind when they were reading and solving the word problem. And students who drew pictorial representations were less likely to correctly solve the word problem than students who were able to draw visual schematic representations as seen on the right. And that is partly due to the fact that in a visual schematic representation, students show the spatial changes of the object and are more aware of what is occurring and are able to better comprehend what is occurring in the word problem. So this is all to show that teachers should use schema construction and emphasize the use of visual representations along with explicit instruction on math vocabulary. So all 3 of these work well on their own, but it is most effective to use all 3 together.
All right, this is not an evidence-based practice. We've talked about this one a lot. After this presentation, you should not have one of these in your classroom because this is setting students up to get tricked. They're not actually doing the word problem correctly because they're not reading. They're cherry picking for these phrases. They're assuming that total sum is going to be related to the operation of addition, which in our past few slides, we saw lots of examples of where those phrases were in problems, but asking for different operations. So when students are using this kind of tactic, they are not working on comprehension, understanding what the problem's asking. They're just looking for these sort of clues to then cherry pick the problem, plop in the numbers and find an answer. So we need to focus really on our schema-based instruction, understanding what these problems are asking going forward in our instruction.
Yeah, so what is an evidence-based practice is using the structures. So we looked at combined problems, but there are only 2 other addition schema that students need to learn, and one of them is compare problems. So an example is this word problem: the small dog has 3 spots, the large dog has 7 spots. How many more spots does the large dog have than the small dog? So they're comparing the large dog versus the small dog, and you put it in this diagram. greater minus less equals difference, 7 minus 3, and you would get 4. The third additive schema is change problems. You start with a number, a change happens, and then you end with a number. So an example is Carly has 3 ribbons. Shay gives her 2 ribbons. How many ribbons does Carly have? You have the start, which is 3. You have the change, which is plus 2, and then the end would be 5. For multiplication, we have ratios and proportions. There are a few, but this one is taught in middle school. And you have this format where you have compared over base, and it gives you the ratio. So an example of this would be, let's say somebody works for 60 minutes and they take 5 breaks. You would see the ratio would be for 12 minutes they work, they take 1 break. And something else to note with these additive and multiplicative schema is that you're also teaching subtraction and division. So here you can see the division in this schema, and then for this one, you can see the subtraction as well. It depends on what the unknown is, and that's the operation you use. For when problems get more complex, they're just like an additive schema or multiplicative scheme together, or like 2 additive schemas together. So these are multi-step problems. And so one example of this is percent change, taught in middle school. And so you can see the change problem up on top, and then the ratio problem. So that's an additive schema with the multiplicative schema. And so if students have a good understanding of those schemas, they can transfer this into a multi-step problem.
All right, so we're going to walk through how you would scaffold kind of a word problem for students, kind of from like the lowest level to the beginning of it towards the end where it's more conceptual understanding of it. So in our first step, we're talking about Letitia has 5 comic books, Riley has 3 more comic books. They have 8 comic books altogether. So in this one, there is no unknowns. You know how many comic books each of these individuals have, as well as how many they have together. So with your students, we're using the part whole method with them. They're identifying the 2 parts, which would be how many comic books each of the individuals have on their own. And then the whole would be how many they have all together. So with Letitia having 5 and Riley having 3, they have 8 comic books all together. So that's the most basic form of our word problem. There's no missing parts. We know all 3 aspects of the equation. So we're really focusing on reading and understanding what the problem's saying and identifying those parts.
And then moving into solving the unknown, you'll have a problem that has an unknown. So Kala has 4 cupcakes, Jaden has 6 cupcakes. How many cupcakes do they have all together? They put it into the diagram, 4 plus 6, and then they have a blank for the unknown, and then they can solve the problem using simple addition.
And then finally, a third step, which can also be used throughout the process, is students explaining how they solve the problems. So the teacher should ask students to discuss how they are solving and/or solve the problem if you're using this at the end. So this encourages students to practice metacognition, which is thinking about their own thinking. And studies have shown that metacognition promotes student learning. An example of how you could implement in this classroom is if a teacher asks a student, explain how you know this problem type was combined.
Cool. And at the end of this presentation, we just want to give you guys a couple questions to think about as we head into our conferences tomorrow. So our first one is, what struggles have you experienced or seen your students experience with word problems? This is just a huge part of math and the dreaded word problem that I see with my students in my own classroom. After that, how might you see schema instruction used outside the math classroom, applying that to other courses or other classes and how that can work outside of math? How do you think metacognition could be used with schema instruction to maximize student performance on word problem solving? And then lastly, do you see any possible challenges with incorporating schema instruction into an upper level element or upper level math class?
Thank you so much for watching our presentation. Here are the references we used. Thank you.